So what we're going to look at in this lesson is the relationship between time and distance. When we're talking about real world scenarios where you have someone walking towards or away from a motion sensor. Coming out of this lesson, what you would like to be able to do is describe the relationship between time and distance when you're looking at a problem. You want to be able to describe the walking that a person is doing in terms of like how fast they're going for how long and where they're starting. And then you also want to be able to take a walking instruction, basically a recursive rule for what a person is doing, and sketch a graph of it based on the information given to you in the recursive rule or using a data table. So before we get started, what I'd like for you to do is to work on the launch activity. So go ahead and pause the video, and you're going to identify which of these graphs match up with A, B, C, and D. So pause the video, and when you're done, press play, and we will go over it. So it says match each graph to a recursive rule and explain how you know. So first problem says start with 3 and subtract 0.3 from the previous term. So from lesson 3.2, we know that our starting value is the same thing as our y-intercept, or the point on our y-axis. And then we also know that when we are subtracting a number, we know that our graph is going to be decreasing or going downhill. So in this case, we're looking for a graph where the y-intercept is 3, so where a point is on the y-axis at 3, and then also decreasing. So that would be graph 2. Next, we have a graph where it says start with 0.8. So again, our starting value is going to be our y-intercept. We're going to add 0.1. That means our graph is going to be increasing or going uphill. So we're going to look for a graph of a starting point of 0.8 and one that's going uphill. That would be graph 1. Next, we're looking for a graph where the person is starting with 0.2. Okay, so again, that's our y-intercept. And we are adding 0.8. That means the graph is increasing. So again, we're looking for a graph with a y-intercept of 0.2 and one that's increasing. So we have graph 3. And finally, that leaves us with one option for letter D, start at 2, subtract. So we're looking for a y-intercept of 2 and a graph that is decreasing. That would be graph 4. Now, letter E sort of asks us to summarize what we already know. It says, how can you tell by looking at the recursive rule if the graph will rise or fall to the left? So again, another word for rise is increase, and another word for fall is decrease. Okay. So looking at these recursive rules, you should notice that we can tell if a graph is going to rise. That is going to happen when we have a rule with addition. And then finally, if it's going to fall, that's going to be a rule that has subtraction. Now, in this lesson, we're going to learn how the starting position, speed, direction, and final position of a walker influence a graph and an equation. So this is sort of your goal here. You want to be able to explain how all 4 of these things influence the graph and the recursive rule or equation for a person that is walking. So over here to the right, we have what is called a time distance graph. And this type of graph provides us with a lot of information about the walk that this person is taking. So the information that this graph right here provides us is that since it is a straight line and it is increasing, what we know is that the walker is moving away from the motion sensor at a steady rate. So again, since this line is straight and increasing, it means that the walker is moving away from the motion sensor at a steady rate. So they're not changing their speed is constant throughout the entire time. The other thing that we can tell from this is that this person started 1 meter away from the motion sensor. And then over the course of 3 seconds, over the course of 3 seconds, this walker traveled to a distance of 3.5 meters away. So 3.5 meters away. So what we know is that this walker, over the course of his walk that lasted 3 seconds, he traveled 2.5 meters. So what we can come up with is a unit rate of his speed. So we know he traveled 2.5 meters in 3 seconds. So if we wanted to know the unit rate for this walker, what we could do is take 2.5 and divide that by 3, and we find out that his unit rate was, he was traveling 0.83, repeating, meters per 1 second. So again, this type of graph, this time distance graph, tells us a lot of information. It tells us his starting point, it tells us his ending point right here. It tells us how long his trip was, how long his walk was, and then we can also figure out his speed. So what we're going to do is we're going to take a look at the investigation now, and we're going to analyze time distant graphs and see how we can use a recursive rule to create our own graphs while also writing stories that, or I guess instructions on how to complete a walk that is graphed. So if we come down here, we have 3 graphs that are that were obtained by students using a motion sensor and figuring and walking either away from or towards that motion sensor. So what we're going to do in step 1, it says write a set of walking instructions for each graph. So we'll take care of that first. If we are looking at graph A, the first thing that we want to do when we're writing a set of walking instructions is we want to figure out where did our walk start. So for letter A, up here, this graph, we started at 2 meters. So start 2 meters away from the motion sensor. And I'm going to abbreviate the word motion sensors with MS. Okay, I don't feel like writing out the word motion sensor every time. So we're going to start 2 meters away from the motion sensor. And then, since this graph is increasing, it's going uphill, all right, we know that we're walking away from the motion sensor. So start 2 meters away from motion sensor and walk away from the motion sensor at, and now we need to know our speed. So to find out our speed, we want to get a either a unit rate or some rate of change that our distance is changing over time. So if we look at this, we want to look for a nice point on this graph. And what I mean by a nice point is if we look at the point right here where it says, let's say that point where x is 2, we have to figure out our y value. But here you're going to kind of guess what the y value is. We don't want to guess. Okay, so that's not a nice point. A nice point happens when you have a point right here where you get 3 seconds have been traveled, or he's walked for 3 seconds, and then he has traveled, or he is at a distance of 3 meters, because that point lines up nicely with that that distance. So we know at 3 meters he's traveled, or after 3 seconds he's traveled 3 meters. So that was a total distance of, so he went up 1 meter, and then that took him 3 seconds. So he's traveling at a speed of 1 meter per 3 seconds. Okay, so our rule, start 2 meters away from the motion sensor and walk away from the motion sensor at a speed of 1 meter per 3 seconds. And we would do this for 6 seconds. Now, if we wanted to, we could rewrite this speed as a unit rate. That unit rate would be 1 divided by 3, or 0.3 meters per second. Okay, and writing it as a unit rate is something that can be beneficial later on, especially in your homework when you're trying to compare which speeds are fastest. So let's take a look at letter B. Again, if we're writing our walking instructions, what we need to do is we need to come up with where are we starting. So first, if we look at this, we see we're starting at 1, 2, 3.5 meters. So start 3.5 meters away from motion sensor. After we have our starting point, we need to figure out if we're walking away from or towards the motion sensor. Since this is decreasing, our distance from the motion sensor is decreasing. Therefore, we're walking towards the motion sensor. So start 3.5 meters away from the motion sensor and walk towards the motion sensor. Now we need our speed at, and then we want to find a nice point. So we know we started here at 0 and 3.5. So if we look at this, if we look at our graph, we see that we have this point right here. That point is going to be, you traveled half of a meter, and then it took 2 seconds to travel that distance. Okay, so we have a speed of half a meter per 2 seconds. Now, we want that, so we could leave it like that, or we could make that a unit rate. So if we wanted to make it a unit rate, we would take 0.5 and divide it by 2. That would give us a speed of 1/4 of a meter per second, or 0.25 meters per second. So we going back to here, we're walking towards the motion sensor at 0.25 meters per second. Now, last thing we need to do is how long are we maintaining this speed? These graphs are going from 0 to 6 seconds, so we maintain this speed for 6 seconds. Now, the next thing we have is this graph over here, letter C. Now you should notice that there's a difference in this graph. The difference in this graph is that there is a section of this graph that goes uphill and a section of this graph that goes downhill. So that means that this person is changing direction. Okay, and he changes direction when the graph changes from increasing to decreasing. So, or from uphill to downhill. So we need to write a story here. So again, we're going to start at 3 meters away from, so start at 3 meters, and then we're going to walk away from the motion sensor because this section is going uphill. Now, we need to figure out the speed. So if we look at this, we started at 3 meters away, and then after this section of the trip, we are now 4 meters away. So we traveled 1 meter in 1, 2, 3, and 4 seconds. So 1 meter per 4 seconds, which is equivalent to 0.25 meters per 1 second. So we walk away from the motion sensor at 0.25 meters per second. For how long? For 4 seconds. Then we change direction. The graph starts going downhill. So then we are going to travel away from the motion sensor. And if we look at that, so then start walking away from motion sensor at what speed? So if you look at this, we have a point of 4.4, and then we have a point of 5.3. So if you look at this, over the course of 1 second, our x value, the distance changed by 1 meter. So we're walking away from, or walking, my fault, then start walking towards, because we are the graph is going downhill. So start walking towards the motion sensor at 1 meter per second for a total of 2 seconds. Okay. Now, this is one of the top 2 goals of what you want to do be able to do after watching this lesson. You want to be able to look at a graph like this and to describe the walk that this person is taking, just like this. Okay, you need to include your starting points, the speeds, and the lengths of time that they are walking. So if we look at these questions in parts A and B, it says, in which of the graphs is the walker walking the fastest? Remember, the faster, so if we want to figure out the place where he's walking the fastest speed, we're looking for the steepest graph. Okay, so in this case, the steepest graph at any point in these 3 graphs is right here. So the graph of the walker in graph C, so graph C is where the walker is walking the fastest, okay, because that is the steepest section of a graph right there that I highlighted in red. How fast is that? Well, we said that it was 1 meter per second at that point. Okay, so that is the fastest that he is traveling. And again, how can you tell just by looking at the graph? It is when the graph is the steepest part of the graph. Okay. Now, the other question that we want to know is which graph did the walker start closest to the sensor? Okay, again, remember, starting point is your y-intercept. So if we look at the graphs where the y-intercept, or if we look at the y-intercepts of the graph, we want to ask ourselves, well, which one is closest to 0? And you'll see that it is graph A at 2 meters. So graph A, because y-intercept is closest to 0, 0. Okay. Now, there are 2 things that we said we wanted to be able to accomplish. Describing the story or the walking instructions when you're looking at a graph, and then also taking the walking instructions and creating a graph. So we're going to look at these examples where we are given the walking story and we need to create the graph. So again, you'll see that it says we start at 2.5 meters. Again, that is our y-intercept. So we are going to start with our y-intercept at 2.5 meters. Then it says we stand still. Think about that. If you're standing still, is your distance changing? The answer would be no. If you're standing still and you are 2.5 meters away from the motion sensor and you're not moving, your distance is staying the same. So after 1 second, you're still 2.5 meters away. After 2 seconds, you're still 2.5 meters away. After 3 seconds, 2.5 meters, 4 seconds, 5 seconds, 6 seconds. And so what you notice is that you have a line that is a straight horizontal line. Okay? So when you have a person standing still, you are going to notice that you're going to have a part of a graph where it is a horizontal line. Okay, that represents standing still on these time distance graphs. Now, let's take a look at letter B. It says start at the 3 meter mark. Again, that's our y-intercept. It says that we're going to walk towards the sensor. That tells us that our graph should be downhill. Then we see we are traveling at a constant rate of 0.4 meters per second. So if we start at 3, after 1 second, we're going to be at 2.6. After 2 seconds, we're going to be at 2.2. After 3 seconds, we're going to be at 1.8. 4 seconds would be 1.4, then 1.0, and then 0.6. Okay, so again, you'll see these should be in a straight line. Since we are human, our graphs probably won't be perfect, so we connect our dots, and more or less we have a straight line that is going downhill since we're walking towards the sensor, and it's a straight line since it's a constant rate. If we look at letter C, we're going to take our walking instructions, and this time they are listed as a table. So we're going to start with at time 0, we have a starting point of 0.8, so right about there. After 1 second, 1.0, then 1.2, 1.4, 1.6, 1.8, 8, and then 2.0. So again, we have a straight line. We have our starting point. My dots and line don't match up perfectly because we are human, but we have a graph that represents these walking instructions. Now in step 3, it asks us, it says, let's compare the tables for 2b and 2c. We don't have a table for 2b, so we need to make that. So if we have a table for 2b, we will write it just like we did for 2c since we want to compare them. So we have 0, 1, 2, 3, 4, 5, and 6. Okay, so the distance we had for at time 0 was 3, and then we had 2.6, 2.2, 1.8, 1.4, 1.0, and 0.6. Okay, and the question in step 3 says, how can you tell based on the table which set of walking instructions, which walker is traveling the fastest? And so in order to figure that out, what we're going to look at is how much the distance is changing per 1 second. So in this case, the distance is changing at 0.4 meters in 1 second. Same thing here, 0.4 meters in 1 second, 0.4 meters in 1 second, 0.4 meters in 1 second. So this is our speed that walker is changing. Next, we look at the distance from the change in distance per second in table C. 0.2, 0.2, 0.2, and so forth. It doesn't matter if we're subtracting or adding. The subtraction sign means the subtraction and the addition that sign tells you which direction you're going in. So we are traveling 0.2 meters per second in table C, 0.4 meters in table B. So table B is traveling faster. Okay, so how can you use the information in the table to determine which graph is steeper? You're looking at the amount of change in distance per second. And this is going to come into play over and over again for the remainder of this unit and for a large part of Algebra 1. Okay, is the amount of change in distance per second. All right, so we'll go ahead and look at these two examples here. So in this first example, it says graph a walk from the set of instructions. Our set of instructions are start at the 0.5 meter mark and then walk at a steady speed of 0.25 meters per second for 6 seconds. So we're at 0.5, 0.75, 1.0, 1.25, 1.5, 1.75, and then 2. So again, since it's a steady rate, it should be a straight line, and our starting point is 0.5. And since it doesn't tell us whether or not we're walking towards or away, we're going to assume we're walking away from, because if we didn't, we would run out of space on our graph in this case. Next, it says write a set of walking instructions based on the table data and then sketch a graph of the walk. We're not going to sketch the graph here. I think with all these examples, you probably have figured this out on how to sketch the graph. You would just plot these points on the XY axis. To write a set of walking instructions, though, we would start at 4 meters from the motion sensor, again, abbreviating it MS, and then we see that we are going down by 0.4 minus 0.4. So since we are subtracting, we're walking towards the motion sensor. So start at 4 meters from the motion sensor and walk towards the motion sensor at 0.4 meters per second. Okay. Now, we have one last example we're going to look at where the walker changes direction several times. We're going to go over these summary questions, and then you will have time to work on the homework. So if we were going to write a set of instructions, we're going to kind of abbreviate these instructions here just so we can save time. We have one section, then we have a second section, and then we have a third section of walking, okay? So we have to write basically 3 parts to this story. So the first section we'll write in green since we highlighted in green. We see that we are starting at 0.5 meters. And we are walking away from, since that part of the graph is uphill. So walking away at a speed. So if we start at 0.5, again, 0 seconds, we're at half a meter already. And then we end right here where it is 2 seconds and 2.5 meters. So we traveled a total distance of 2 meters. The distance from 0.5 to 2.5 is 2 meters. So 2 meters in 2 seconds. If we simplify that, that would be 1 meter per second. Okay, so walking away at 1 meter per second for 2 seconds. Then the walker decides he needs to change direction. Maybe he forgot something at home. Okay, so we see that he's traveled for 2 seconds. He's at 2.5 meters away, and then he needs to turn around, and now we're at 4 seconds and 1 meter. So he turns around and walks towards the motion sensor and we got to figure out the speed. So he travels from 2.5 meters away to 1 meter away, so that's 1.5 meters, and that took him a total of 2 seconds. If you simplify that, 1.5 divided by 2, you get 0.75 meters per second. So he walks towards the motion sensor at 0.75 meters per second. For how long? For a total of 2 seconds. Finally, this walker gets whatever he left wherever he left it, right here, and now he's going to start walking away from the motion sensor again. So he turns around and walks away from the motion sensor, and we have to figure out that speed. So he's at 4.1 and then he ends up at 6.3. So he traveled a total of, he traveled a total of 2 meters. So 2 meters, and he did that in 2 seconds. So again, that would be 1 meter per second. So it walks away at 1 meter per second for 2 seconds. And that is the story of this person's walk. Now, to summarize what we have talked about today, because there was a lot in here, there are some key things that you need to take away. First off, in graphs of walking, which axis represents which variables? The x-axis is going to represent your time. The y-axis is going to represent your distance. That's how it's going to be every time you deal with this type of problem. Next, the question says, how does the graph relate to the movement of the walker? And so what this tells us is the height. So in this case, the height tells us how far the walker is from the motion sensor. Again, motion sensor is abbreviated MS. Next, it says to make the graph rise, what walking instructions did you give? To make it rise, we said walk away from motion sensor. To make it fall, walk towards the motion sensor. And then finally, to make the graph steeper, we would tell that person to walk faster. Okay, if we wanted to Tell them if we want to make the graph less steep, we would tell them to walk slower. So that was a lot of information. You should hopefully be able to feel comfortable after doing the homework in terms of writing a story to match a graph and to graph matching a story. So you're going to work on your homework. If you have any questions, message me on Remind or on email. See you in class.